So would you like to wait a little bit, other participants, or shall I start?
I think you start. So today we have Gianluca Faraco from Max Planck Institute, Bonn. He will be talking on the Riemann surfaces with many automorphisms.
Okay, so thanks for the introduction, Devendra. Well, so the idea today is to discuss this Riemann surfaces with many automorphisms. So first of all, we should say what a Riemann surface is, so let me introduce them. So Riemann surface. This can be seen. A Riemann surface X is one-dimensional complex manifold. And this means maximal atlas of charts. So we have this atlas, a collection of pairs U alpha, phi alpha, where alpha lies in some set of indices. And our Riemann surface is equal to the union of this open set U alpha and our functions phi alpha take values on the complex plane. These are our charts, and we require that phi alpha, the phi beta inverse, depending on phi beta or U alpha, okay, U beta. We want that this change of coordinates is a bilomorphism. Okay, well, so it's a standard fact that one can find on Miranda's book, for instance. Fact, see proposition 1.23 from Miranda. So it says that any compact Riemann surface is okay. So let me any Riemann surface is non-orientable to manifold. And assume that our Riemann surface is compact in addition. Let's go back. Then we can call this Riemann surface X, for instance. Sorry, say X. Then X is a closed surface of genus G, orientable surface. Well, let's see some examples of these Riemann surfaces. There are some very standard examples. So the first one, the very first one is C is a Riemann surface. And And this is pretty easy. This is trivial. There is one global chart. If we pick C and the identity on C, this is a global chart. So one chart suffices for finding such an atlas. Second example, slightly less trivial, but still an easy example, is the Riemann sphere CP1. It's the Riemann sphere. This can be seen as C union the point at infinity. So this is basically one point compactification. Here you can find an atlas with exactly two charts. One is C and the other is the complement of the origin in CP1. And the function is just, okay, we can find the atlas. So our atlas is given by two charts, C and the identity on C, and the other chart is CP1 minus the origin, and the function is 1 by Z. Oops, 1 by Z. This is our atlas. Third example that I want to introduce, but it will be important later. This example is what we call H. This is a set of complex numbers such that their imaginary part is strictly positive. Let me introduce a less trivial example now. And this is set X, which is defined as couple XY in C2, such that X to the power n plus Y to the power n is equal to 1. This is an important Riemann surface. This is called affine Fermat equation. Sorry, not equation, CARP. Affine, because this is defined by an affine equation in C2. And what is the Riemann surface? So I won't go through the detail too much, but there is something that you can find on Miranda, for instance. We have this definition that an affine CARP is the locus of zeros in C2 of some polynomial fxy equal to 0. We say f is not singular at a point P if the partial derivative of f with respect to x at P is different from 0, or partial derivative of f with respect to y at P is different from 0. Now there is this proposition that if f xy in C xy, this polynomial, is irreducible, I can write it here, irreducible, and non-singular means that for any point in the zero locus, that point is not a singular point. So one of the two partial derivatives is not 0. Then the set of the zero locus. So they play the set of points xy such that fxy is equal to 0 is a Riemann surface. And so from this proposition, it sounds clear that Riemann surfaces are abundant. There are a lot of reducible polynomials, and each one of them provides an example of Riemann surface. Another example is given by the following Riemann surface, which is strongly related to the one above. X, Y, Z in CP2 such that x to the power n plus y power n is equal z to the power n. And this is what we call projective Fermat equation. Sorry, car again. So this is the projectivized version of the equation above, but we can also derive the following as from the same book of Miranda. One can see that the set of f x y z equal to 0, where f is an homogeneous polynomial now, because we are things in CP2, so we have homogeneous coordinate, and we have to use homogeneous polynomials. Is a Riemann surface. And in general, there is a standard fact, this is a very important fact, something that let me call that as a theorem, and I'm not going to prove it here, but it's something known, and maybe it's one of the most important notions about compact Riemann surfaces. So if we consider a set of compact Riemann surfaces,
this f would be irreducible homogeneous polynomial in this case also, right?
Yes, this should be, yeah, that's a good point. Thanks for the question. So, okay, let me do it like this. Yeah, here f has to be f just okay. The f is non-singular. Yeah, this is an important notion that I was going to forget to say. Is non-singular if x defined. Okay, so the okay, I can say it this way: if and only if. Then I'm going to explain notation. If and only if the curve xi defined as x intersection ui is a non-singular curve. And here we want this guy to be non-singular. So what are these objects? So x here is just our set f equal to 0. And ui in CP2 u high, it's just a set of say x. Okay, we have this triple x1, x2, x3, where I'm slightly changed the notation actually, but sorry, but xi is different from 0. So we can say ux if the first coordinate, the x coordinate, is different from 0, uy if the y coordinate is always different from 0, and uz if the z coordinate is always different from 0. So these are like these are copies of C2. These are kind of affine copies of C2 inside the projective space, CP2. So if, and we define xi, define this guy here, xi, just as the intersection of our compact car, because CP2 is a compact space. This is a closed set because it's defined by an equation, which is so something closed. A closed subset in a compact space has to be compact, so X is compact. And the intersection of this compact guy with UI provides a non-compact car in some affine space, homomorphic, actually biomorphic to C2. And so Xi is an open Riemann surface. And Xi is just an affine car as defined here. So whenever you have the projective version, you say that defined by some non-singular polynomials, then you have a compact Riemann surface, which is basically the compactification of this guy here. Yeah, we need this non-singularity property, otherwise that's not simply true. So thanks for asking. What I was saying is that there is this one of the most important theorems about compact Riemann surface. Yeah.
This notion of non-singularity, is it not equivalent to partials of capital F with respect to x, y, z are not simultaneously 0 at any point in that projective space?
No, I mean, the intersection xi has to be a non-singular curve. It means that the partial derivative cannot be all equal to 0. It cannot be all 0 at the same at some point at the same moment. I mean,
yeah. So instead of taking, yeah, but capital F, you have to divide by z or something, right? How do you make it that as an affine curve?
Yeah, you dehomogenize the equation.
So I think if you just take f as a polynomial in 3 variables.
In 2 variables. I mean, f capital F has 3 variables.
Take partial derivatives.
Yes. Okay.
That with f equals 0 doesn't have a common solution. The partial derivatives also do not vanish at the point where f is 0.
Sorry, I'm
capital F sub x, comma capital F sub y, capital F sub z is not at any point p where capital F is 0, that 3 partials should not be simultaneously 0.
No, exactly. They cannot.
So
they cannot.
Yes, so that's a quick way. Besides going to UI, instead of going to UI and then considering this.
Yeah, I mean, I'm just taking these definitions from Miranda's book.
Yeah,
and
yeah,
the way
anyway.
he
okay.
he proposed yeah, I mean, he develops the theories in this way, basically.
Because capital F equals 0 can be considered as a cone in CP3.
Okay.
And that origin is not there when you go to CP2. So those rays there, they will have some, they're simultaneously non-singular. I mean that way. So yeah, anyway, these are the concrete ways of checking something is non-singular. Yeah.
Yeah, but I mean, there is a way from moving from one definition to the other, basically.
Okay.
So,
all right.
say that, I mean, one can even begin with this projective curves. So you can think the locus of zero, I mean, locus of zero is some homogeneous polynomial.
Yeah.
And then you have some projective curve, which is something close, it's compact, it's a compact Riemann surface. But then yes, if you, the point is that we have this compact surface in CP2. We fix one coordinate, which is the set of all triples, where, let's say, one of the three coordinates is always different from zero, so we can dehomogenize with respect to that coordinate. And after dehomogenization, you get an equation, something like, okay, in the case of Fermat curves, we get something like this, but if you have some generic capital F, you get an affine equation. You have an affine model for that curve, which is no longer compact because it's defined on C2. That's it. But the point is that capital F is set non-singular if you if the curve that if you dehomogenize with respect to all coordinates,
Yeah.
all the curves you get are non-singular. That's the idea. I hope it's more clear now. So, so the theorem I want to mention, without going through the proof of the theorem, is that compact Riemann surfaces. There is a one-to-one correspondence between compact Riemann surfaces and smooth projective algebraic curves. So curves which are defined as by an equation f x, y, z equal to 0 in CP2. And this is one of, say, main theorems in the theorem of Riemann surfaces.
No, that's not true. One direction is true. If smooth projective curves are compact Riemann surfaces.
Yes.
But every compact Riemann surface cannot be obtained as a smooth projective algebraic curve in CP2. It can be obtained as a projective curve in CP3.
Yeah, I guess that's also the reason. I mean, like his definitions. Okay, maybe he did it for CP2, but
a smooth projective curve in CP2. If that capital F is of degree D, then the genus is D minus 1 times D minus 2 by 2. So the genus is restricted.
You can get all possible genus. Yeah, okay, I got it. Yeah. So, oh, this is true in CP3, but
in CP3 it is okay.
Okay.
In CP3 it can be embedded, but yeah, this is the kind of Kodaira embedding theorem here.
Okay. Right. I don't know to write
Kodaira embedding theorem is for all. No, I think it's something more than that.
Yeah, because in CP2, yeah, this degree genus formula, yeah,
is for higher dimensions. So which compact complex manifolds can be embedded in CPN for n large? That is done by Kodaira's embedding theorem, and there's a condition on the compact complex manifolds for that.
Perhaps this is CPG plus 1, if I'm not mistaken. CP to the power G plus 1, maybe. Might it be? I mean, maybe the dimension.
No, it's the same. In 2D plus 1, if compact complex manifold of dimension D satisfying a certain Kodaira condition
Mm.
can be embedded in CP 2D plus 1.
Okay. Okay, I had in mind this thing about CPG plus 1, but maybe my
No, so far as D equals 1 is concerned, compact Riemann surfaces, they can be obtained as smooth curves in CP3. And then from CP3, from a point not on the surface in CP3, you can project them to CP2, but it will develop some singularities.
Okay.
And generically, there are double singular, there are double points.
Okay. Okay.
That's a generic case. Non-generically, many things can be done. That's a big industry.
Yeah. Thanks for pointing me out that. Yes. I was speaking CP2, but yeah, that's true. CP2, there is this degree genus formula that basically is not all possible genus can be achieved. Yeah, that's
Fulton's books or Fulton's notes, W. Fulton's notes. They clarify this.
Okay. So who has written these notes? Can you say again the name?
Fulton, FUL, I will tell you.
Fulton. Okay.
Famous book, Algebraic Curves.
Algebraic curves. Okay.
The older book was Walker by Walker. I studied this subject from Walker.
Yeah, because I studied this theorem from another book, Miranda and maybe another. Now I don't remember which. There's another, maybe Foster. I don't remember. There's another book on Riemann surfaces. But yeah, okay. So what is true is that any compact Riemann surface can be seen as a smooth algebraic curve. I just what was wrong is that the space was wrong. It's not CP2, but in
when
CP3.
they say smooth projective algebraic curve, they mean the dimension is 1, but
no, but it can be embedded. Yeah,
but it is embedded in possibly higher dimension.
Yeah.
Yeah.
Okay.
Not in CP2.
Thanks for a correction.
Yeah. You're welcome.
Okay, so now there's this point about we want to spend a few words about uniformization. So there's this theorem. It says that Riemann surface X is simply connected then X is 1 or the following. So X could be X is either first case is the complex plane itself, or it could be the Riemann sphere, or in the latter case could be the Alcaraz plane. So the first one of the 3 examples I've mentioned at the very beginning. And so this is one of the theorem concerning the uniformization theorem. And so, okay, let me now introduce the following definition of automorphism group. So let X be Riemann surface. So we define out X as the subgroup of orientation preserving homeomorphisms of my surface. So this guy here is concerned the topology and not the complex structure, such that F in out X is a bilomorphism. And this can be seen in local charts in the sense that if you pick a local chart, two local charts, so okay, let's say, so you pick some open set U and let V the image of U via F. I look at their images via local charts, and what I want is that this guy here is a bilomorphism. If this holds for any charts, then we say that F is a bilomorphism for our Riemann surface, bilomorphism. Some examples even here. What time is it? Okay, some examples. In the case of the complex plane, out C is just the set of translations on CP1, the group of automorphisms is nothing but PSL2C. And this is very nice. This is a very
out C is Z goes to AZ plus B, where A is not 0.
Sorry, where?
Out C. You had admitted translations, but also homotheties. Z goes to AZ plus B, where A is not 0.
Right. Yeah.
Yeah.
This is C star.
Right.
Semi-direct C. Yes. Yeah, indeed, here in my notes, I wrote a fine mappings. I don't know why I wrote a translation here. Sorry. And in the case of the Alcaraz plane, this is less easier to check, but one can see this PSL to R. Well, now another part of the uniformization theorem, so another theorem says that Riemann surface X can be seen as the quotient of Y, where Y is one of C, CP1, or Alcaraz plane by the action some group gamma, which is a subgroup of out Y. And the action of gamma is properly discontinuous and free. Means that the group gamma is torsion free. There are no elements of finite orders. Okay, so now there is the following discussion. So let X a Riemann surface and let X tilde its universal cover. So in particular, we have the covering projection pi from X tilde to X. They said that the group of automorphism of X is the group of mapping from X to itself. These are biomorphisms. What do? We let F tilde a lift of F to X tilde, the universal cover, which by the uniformization theorem, this guy here could be just the complex plane CP1 or the Alcaraz plane. And so F tilde is an automorphism. Okay, I can briefly write it in this way. So tilde belongs to out X tilde. And it commutes with the action of gamma, where gamma is the group that uniformize X. So namely, it means that X can be seen as X tilde mod gamma. And this, to say that F tilde commutes with gamma means that this commutativity means that F tilde gamma is equal to gamma F tilde. Or if you like diagrams, what is happening is that here we have the covering projection. Here there is the mapping F to itself. Here is another covering projection, and this guy here is F tilde. So the point is that an automorphism of a Riemann surface is determined from an automorphism of its universal cover, but this automorphism is an element of that commutes with the entire group. So it means, this means that F tilde F belongs, sorry, not F, F tilde belongs to the normalizer of the group uniformizing our Riemann surface. And in fact, one can, it is possible to show, it is possible to prove that for a Riemann surface X seen as gamma mod X tilde, then the automorphism group of X is isomorphic to the normalizer of gamma mod gamma as a group. And gamma is a normal subgroup of finite index in this guy. Not necessarily finite index, but these are normal subgroups. So this is indeed a group which is automorphic, isomorphic to the group of automorphisms of the Riemann surface in itself. Let's focus on the case. Let's consider. Now I have other 20 minutes or so, so let's consider G at least 2. So Riemann surfaces on topological surface of hyperbolic type. Hyperbolic type means that the other characteristic is negative. Well, so for these surfaces, so here it is, fact, if X is a Riemann surface of hyperbolic type, then X tilde is the upper of plane. And so gamma is a subgroup of PSL2R acting freely and properly discontinuously, where gamma is the group of uniformizing X, so X is equal to gamma mod X tilde, gamma mod H. Okay. Sorry, just how's my tablet? Okay. So this group this is defined. This is called actually function group. This is another fact that if gamma is a function group, then the normalizer of gamma and is a function group, and here we have to show I think we have to say and non-abelian. Otherwise, I think there are some counterexample. Then the normalizer of gamma is a function group. Okay, we are now ready to introduce surfaces with many automorphism, which was the main topic. I mean, the main object to discuss. So, a Riemann surface has many automorphisms if we should choose X, if X can be seen as gamma mod ace mod gamma, where gamma is a function group. Say gamma is a function group, and in particular, gamma is a normal subgroup into some triangle group. And these Riemann surfaces are called quasi-Platonic.
Quasi-Platonic.
It's actually now the main theorem here is that X is quasi-Platonic if and only if X is the quotient of H mod some group gamma, and its normalizer is a triangle group. This is also equivalent, even is also to the existence of some mapping that we call beta from C to CP1, which is branched covering with 3 ramification points. And so we don't have enough time for discuss this kind of mappings, but beta is so-called Bailey map. Okay, so surfaces with many automorphisms, these so-called quasi-Platonic surfaces are so.
I think not every Bailey map correspond to this general triangle group. As you said, it should be a normal subgroup of the triangle group. So this should be a Galois Bailey map. There should be some condition on your coverings.
Okay, I'm not sure about the terminology because you're right. Someone called this kind of mappings Galois Bailey, but when I was taking my notes, looking at this Wolfert book, Garrett Johnson Wolfert, Garrett Wolfert book, they call it Bailey map.
Okay.
So anyway, what matters is that you are quasi-Platonic if this Riemann surface has so many automorphisms so that if you look at the quotient of this X mod, so
I'm just trying to draw conclusion from your definition and the previous talks that happen in the series. Like you are saying that it should be normal subgroup of the triangle group. So they correspond to a spatial Bailey map, which are called Galois Bailey. Okay. Anyway,
now I'm confused because I'm pretty sure that from this book by Wolfert.
we can discuss later. You can finish your talk first.
Yeah, okay, we can discuss later. So I was just checking from where I copied this. Till now I don't find the statement. Okay, anyway, that doesn't matter. So the point is that a surface is called quasi-Platonic as a very large group of automorphisms, in the sense that if you look at the quotient X mod out X, this is a topological sphere. This is a sphere. So you have so many automorphisms that doesn't matter what's the topology of your surface X. You have so many automorphisms that the quotient has no topology, it's just a sphere. That you say very large, so many automorphisms, Riemann surfaces with many automorphisms. The final question before concluding is that question. Is given a Riemann surface X, what is out X? So generally, let me say for almost all Riemann surfaces in some sense, the automorphism group is trivial. In the sense that if we think the space of moduli space of all complex Riemann structures up to biomorphism, this carries a measure, and with respect to this measure, almost all Riemann surfaces the group of automorphism is trivial. But there are some special Riemann surfaces where the group of automorphism is larger. And so what's the cardinality? There is this theorem by Hurwitz that says that the cardinality of out X cannot be greater than 84 G minus 1. And so there is a geometric proof. This basically one. Now I don't have enough time for explaining the proof, but there is a geometric one for explaining why this bound is sharp. And in this sometimes it's also achieved. So for genus 2, there is no Riemann surface such that the group of automorphism has cardinality 84. So there is one Riemann surfaces and Riemann surface, and I don't remember exactly the equation, but it's called Boltzmann surface. I think that in a fine coordinate, the equation should be x squared equal to this should be the equation of the Boltzmann surface in the affine equation, so in C2. And this has exactly 48 automorphism. And it is the most symmetric in genus 2. In genus 3, instead, there is only one Riemann surface such that, say X, okay, no, okay, called Hurwitz surface, says that the group of automorphism has cardinality exactly 168. So it achieves the maximal bound. Indeed, if you plug 3 here, instead of in place of G, you have 3 minus 1 is 2 times 84 is exactly 168. And this can be written explicitly. So this surface is x cubed z plus y cubed. Or maybe this is y cubed z plus z cubed x equal to 0. Sorry. And then this kind of surface that they achieve the maximal bound are pretty rare. So for G equal to 5, 6, 4, 5, 6, there are no such a surface. In genus 7, there is one. It's called. There is one called. I think it's called Macbeth surface. I don't know exactly what to say. Macbeth surface. And so these are kind of pretty rare surfaces, but there are. Well, I think that if I continue, okay. I want to mention just the very last. The very
You can
last.
continue, it is not at PM. You can continue maybe 5 more minutes.
Yeah, but I think I conclude just mentioning this curve that is called F4, which is this is a Fermat curve. With n equal to 4, and this according to the book of this book by Jones and Wolford, one can see that F4 is quasi-Platonic. And okay, so
What is genus and size of its automorphism group?
yeah, let me check, because I noticed that I didn't write it, but I can tell you immediately because I remember where I took this information. Genus 4. No, this is genus 3. Sorry. 5.10. Okay, there is a table. There is a table, and so the table that is not really clear to me how to read it, because there are basically 6 groups, and I don't really know which one of them corresponds exactly with the automorphism group. But I mean, they are kind of combination of some semi-direct products of groups, so it's nothing simple or easy to to understand it. But okay, so I think I'm stopped here for my talk today. So maybe perhaps at some point we can discuss further about this kind of surfaces if you want. But for today, I think I've stopped here.
Okay, thanks. Anyone has any questions for Luca?
Do you know the literature on this? There's a vast literature.
Mm. Yeah, the literature is, yes, there are a lot of papers, a lot of things has been written about this surface. There are a lot of connections with these triangle groups. There are connections with even with some kind of number theory somehow. Even because, for instance, for these surfaces with many, Hurwitz surfaces, after genus 7, there are 3 in genus 13. And there is some kind of number theoretic property for recognizing which Riemann surfaces are Hurwitz. But that's something that's not my area of expertise, so I don't know exactly how to move in that direction. But yeah, several things has been written. Yeah.
By chance, do you know my important paper in this?
Sorry?
By chance, do you know my important paper in this direction?
There is your paper about PQ2 tessellations of Riemann surfaces.
About the automorphism groups.
And you wrote a lot of papers. So which one are you talking about?
No. Extremal Riemann surfaces.
No. surface
Large automorphism.
symmetries of, not large, basic
Symmetry of surfaces.
surfaces, symmetries of surfaces, I think,
Symmetry of surfaces.
in topology.
Yes, in that article, you actually discuss the stable upper genus property of the group also, I think.
Yeah, so
But is a paper that you have co-authored with Edmonds, maybe?
No, it is single author paper.
Oh, singular. Okay, maybe.
I just asked the question. The questions were, given a genus, consider all Riemann surfaces and consider their automorphism groups. That question is more complicated in the Teichmüller theory sense.
Mm.
But if you ask the reverse question, that given a group on which genera it acts, then it has a better answer.
Okay. Okay.
So given a group, you can actually say something very specific in terms of its 2-0 subgroup,
Mm.
which genera it can act.
Okay.
So
Okay.
Actually, I read that paper and I also cited your paper in my first paper. I am very thankful to you for that paper.
So one has to know a lot of finite group theory to make further progress in this. And now you can define what is large automorphism group. That is up to you. And then there is some classification and so on.
Mm.
And it accounts for Riemann surfaces of low genera. Many of them, they appear, and their algebraic equations also appear. Yeah, it's a fascinating story.
Yeah, definitely. Definitely. But indeed, I'm reading now this book by Jones and Wolfert.
Okay, now I'm not...
And I mean, I'm enjoying that book. I mean, I'm reading that in my spare time because I mean, for doing research and other things,
okay.
I just got a little time during the evening, so I'm proceeding a little bit slow. But I mean, I'm enjoying that book. I'm reading this theory and a lot of papers. I mean, and after every chapter, there are several papers cited. I mean, it would be nice to go through the papers at some point, but I mean, I have not enough time for doing that. So, a lot of things to read, but the topic is very interesting in it. Yeah. But I mean, there is a paper of mine where I somehow related complex projective structures to quasi-Platonic surfaces, in the sense that I have this paper where we consider this complex projective structures, which is an extension of Riemann surfaces. So a complex projective structure is like CP1 structure.
Yeah.
Okay.
Yeah.
And so in that paper, with my collaborator, we were considering this problem of given a CP1 structure, determine how many. Okay, let me say one first thing. When you have a complex projective structure, CP1 structure, you have an underlying Riemann surface, and any projective automorphism, so some diffeomorphism that preserves the CP1 structures automatically preserves the underlying complex structures.
Yeah.
And so from this observation, you can say that there are at most 84G-1 projective automorphisms. And in that paper, we count how many projective automorphisms there are for a fixed complex projective structures. And it turns out that if you consider the Fuchsian uniformization of some so like so the functional uniformization of some complex projective structures, then the projective automorphisms are exactly those like complex automorphism. And then we found connections with these quasi-Platonic surfaces. This is that the functional uniformization, if the only one was the number of projective automorphisms is equal to complex automorphisms, if and only if the underlying Riemann surface is has many automorphisms. So it's a quasi-Platonic surface. So we have found this kind of interesting connection with this other topic in geometry structures. So that's a paper that, I mean, I think that is, I mean, maybe it's the only paper is not cited yet, but we found that very interesting because we started from this problem in geometry structures, CP1 structures, and we landed on this theory of surfaces with many automorphisms and descendant fan and so on. So yeah, it's surprising how many connections this topic has with other areas of mathematics.
Anyway, let's thank Luca for your wonderful exposition.
Thanks to you for the invitation again. And sorry for that mistake at the very beginning. So
it's okay.
Yeah, thanks.